Hello, this is Dr. Zulfikar Kassam. Thank you for joining us once again. A very warm welcome to you to the continuing series of lectures on the data communications and networks. We are now at lecture number 20. We are working on section number 3, lecture 20. So thank you for joining us. If you haven't had a chance to look at our other lectures, please do so and give us some feedback, some comments that we highly appreciate it. Thank you so much, and spread the word around. So we'll continue on talking about frequency and period. Yeah, period T refers to the amount of time in seconds a signal needs to complete one cycle. Right. So once again, period T refers to the amount of time in seconds a signal needs to complete one cycle. The frequency, on the other hand, refers to the number of periods, so number of complete cycles that is completed in 1 second. So note that period and frequency are just one characteristic defined in two different ways. So period is the inverse of frequency, right? It's important to understand this. The period is the inverse of frequency, and frequency is the inverse of period. So if you look at the formula, the frequency is equal to 1 divided by the period. The period, as we mentioned, is the amount of time it takes to complete one cycle. So the frequency is measuring the number of cycles we can complete in 1 second. Conversely, as you can see here, the period is equal to 1 divided by the frequency. So if we look at like common numbers that you may come across, right? If it takes 1 second, if the period is 1 second to complete one cycle, that means the frequency is 1 hertz. On the other hand, if the period is 10 to the minus 3 seconds, so basically 1 millisecond, that means it takes 1 millisecond to complete one cycle, then the inverse of that becomes the frequency, which is going to be 1 kilohertz, which is 10 to the 3 hertz. If the period is 10 to the minus 6 seconds, so this is a very small period, obviously 10 to the minus 6 seconds, which is a microsecond, then the frequency is once again the inverse of that. So this is going to be equal to 1 megahertz, so 10 to the 6 hertz. If the period is 10 to the minus 9 seconds, which is a nanosecond, then the frequency is going to be 1 gigahertz, or 10 to the 9 hertz. And similarly, if the period is going to be 10 to the minus 12 seconds, or 1 picosecond, then the frequency is going to be 10 to the 12 hertz, or 1 terahertz. So let's look at one quick example. For example, power at home. The power we have at home has a frequency of 60 hertz. Mind you, this is what it is in America. You'll find that in England it will be 50 hertz, and different countries in Europe may most likely have 50 hertz as well. And if you're in Asia, most likely you're going to get 50 hertz as well. In America, it's 60 hertz. The period of this sine wave can be determined as follows. So the period is equal to the inverse of the frequency. If the frequency is 60 hertz, the period is going to be 0. We divide 1 divided by 60, and the answer is going to be 0.0166 seconds. Or if we put this in milliseconds, this is going to be 16.6 milliseconds. Let's do another example. The period of a signal is 100 milliseconds. What is its frequency? First, we convert the period to be in seconds. Therefore, the period of this signal is going to be 0.1 seconds. So we have converted the 100 milliseconds here into 0.1 seconds. Then the frequency is equal to 1 divided by period in seconds. So it is 1 divided by 0.1 second, which was the length of the period, which is equal to 10 hertz. Now, having talked about frequency, we've talked about amplitude before. Now let's talk about the phase. The phase describes the position of the waveform relative to time zero. If we think of the wave as something that can be shifted backward and forward along the time axis, the phase describes the amount of that shift. It indicates the status of the first cycle. So here are three sine waves with the same amplitude and frequency, but different phases. If you look at this first sine wave, it starts perfectly at time 0, the amplitude is 0. And then it starts from there, it starts increasing the amplitude, it reaches its peak value, and then comes down back to 0, and then continues back in a reverse direction. You can see that because the time 0 indicates its amplitude as being 0 as well, the phase is considered as 0 degrees. It is perfectly aligned with what a sinusoidal wave will be. In the second diagram in here, you see that the phase of this wave has shifted. Now the amplitude is at its maximum level at time 0, right? So the wave actually starts here at quarter of its period. The period is t, and this is the quarter of that period, right? So the full sine wave is here, and this is a quarter of that. So the phase shift is quarter time its period, which is basically considered as 90 degrees phase shift. Then the third sine wave indicates that the value is 0 at time 0, so the amplitude is 0 times 0, but now it's actually moving in the downward direction when it is crossing 0 versus moving upwards. So this is considered as a phase shift of half t, or 180 degrees. Now, how is phase measured? Phase is actually measured in degrees or radians. So the previous diagram, I showed you the phase shift of 90 degrees and 180 degrees, right? So here, this diagram shows something very similar as well. Its value in degrees as well as radians. If there's a phase shift of 90 degrees, that's basically pi over 2 radians. If there's a phase shift of 180 degrees, as we saw in the previous diagram, then that is considered as being equal to pi radians. Okay. So you see this 360 degrees is 2 pi radians, 180 is pi radians as you see here, and 90 degrees is half a pi. So conversely, 1 degree is equal to pi divided by 180 radians, or 1 radian is equal to 180 divided by pi. Okay. So if we look at the previous diagram once again, but now keeping into context the value in radians, this is the phase measured in degrees and radians, and you can see once again the shift that we had shown before is 0 degrees on the first diagram. It's in perfect alignment or perfect synchronized way here, while the phase has been shifted by 90 degrees on this diagram and 180 degrees in this diagram here. So coming back and trying to kind of dwell a little bit on this concept of a phase shift of 90 degrees, which is pi over 2 radians, corresponds to a shift of 1/4 of a period, which is shown over here. 90 degrees, a quarter of a period. A phase shift of 180 degrees, which is shown in here, is equal to 180 degrees phase shift. If there's a phase shift of 360 degrees, this will be 2 pi radians. This will be like the whole wave has shifted. Okay. So let's do an example here to illustrate how and when we use these phase concepts, right? So example in here is a sine wave is offset by a 1/6 cycle with respect to time 0. What is the phase in degrees and radians? So if we understand that one complete cycle is 360 degrees, right? Therefore 1/6 of the cycle is going to be 1/6 of that 360 degrees, which is going to be equal to 60. And if you want to convert 60 degrees phase shift into radians, right, this will be 60 multiplied by 2 pi divided by 360 radians, which will be equal to pi over 3 radians, right? Pi is roughly about 3.1422 over 7 to be exact, and this will equate to 1.047 radians. So pi is 3.14159 over here, or 22 over 7 to be exact, and then 2 pi is equal to 360 degrees. Okay. This diagram shows the sinusoidal wave at time t, at any given time t, and this shows you the same wave after the period of the wave has passed, which is, it period of the wave is when it completes one cycle. Okay. And this is the direction of propagation. Now when we draw this wave as a function of time, this is how it looks like. However, in engineering, basically it's more useful to draw the wave in terms of not only its variation with time, but draw it on a different scale where you have the amplitude and the frequency of the wave cell. Now this is a very different perspective of the same information. Right? You have a wave here which is traveling at a certain speed and has a certain amplitude, right? A frequency is 6 hertz, so it completes 6 cycles in 1 second, right? Number of cycles it completes in 1 second is the frequency of the wave. The frequency of this wave is 6 hertz, so it completes 6 cycles in 1 second, right? But if we have to depict the same information in a different context, in which now we draw frequency as the x-axis and amplitude on the y-axis, this wave has a fixed amplitude. It doesn't vary in amplitude, this one. There are waves that do vary in amplitude, and this is why we want to depict this information in a more useful way, because it's easy to describe this wave with a single amplitude over here, because we have one amplitude and we have a singular frequency. In reality, in life, you will see that the wave changes frequency, like when we speak. When we speak, we have actually a voice that emanates with different frequencies and different amplitudes, right? And ideally, we would like to study that. So this is the most simplistic form for the moment to try and focus on frequency variation versus amplitude. But this is a simple one. Okay. So what we would like to derive from this conclusion here is that we can depict a wave which is very simple, but we can describe more complicated ways, which we'll look at later, in terms of frequency versus amplitude. So in the case where the frequency is constant, which is what it is here in this wave, we have a single line with an amplitude of 5 volts. So the important conclusion we would like to make over here is that a complete sine wave in the time domain that you see here, this is the time domain, so the amplitude varies as a function of time, can be represented by one single spike in the frequency domain. Okay? And this is the concept that is leveraged in communications. So we'll do one more slide today, and then we'll continue on next time. Now, if we see a more complicated wave in here, right, or sets of waves, here we have 3 different waves described. One with frequency 0, amplitude does not change in here, it's constant amplitude, frequency is 0. Here the amplitude is constantly changing, the frequency here is 16, and then you see the pink wave, the frequency of which is 8, so it completes 8 cycles in 1 second. You have the green ones complete 16 cycles in 1 second, and then we have the one in which the amplitude remains constant, so the frequency is 0. Now once this information in here of these 3 waves starts to get complicated, as you can see there are 3 different waves in here. When you draw this in the frequency domain, which means the frequency is the x-axis and the amplitude is the y-axis. Now you can easily describe these complicated sets of waves in three simple spikes, right? You have a frequency of 16 where the amplitude is smaller. As you can see here, this is a smaller amplitude in here. Then we have a wave of 8 hertz with the frequency, with the amplitude of 10, right? And then we have a constant wave, the amplitude of which is 15, but the frequency is 0. So now we have depicted something fairly complicated in the time domain in a very simplistic way in the frequency domain. Thank you for watching, and I hope you can join us next time. Take care. Have a wonderful time. It's 2026 almost. A few days away from 2026. Wishing you all a very, very happy new year and a very successful 2026. Hope to see you next year. Enjoy your break and take care.